let's discuss using integrals to calculate volume. In this section, we're going to be talking about finding volume by creating slices, computing the volume of those slices, and then using an integral to add them up. So if we have a solid that has cross sections that all have the same shape, so for example, in my picture here, my solid has cross sections that are all triangles. What we could do is we can slice this region up and compute the volume of each slice and then add those slices up. So in this case, each slice is a little triangular prism. And we could say that the area of the face of this triangle is A of x, and the width of this little prism is actually a delta x. That's because my cross sections are all perpendicular to the x-axis. So if you think of this as like a loaf of bread, the thickness of each slice is actually a change in x, or a delta x. If we apply the limit process, if we compute basically the volume of each of these little slices, which would be a sub x, this area, times delta x, and we let delta x go to 0, then we're going to end up getting this integral right here. So the volume of this object is going to be the integral of a of x dx. Again, the idea is this integral is actually adding up the volume of each of these slices. And we'll integrate from x equal a, where we're starting, to x equal b, where our object is stopping. So let's see how this works by looking at an example. The base of an object is a triangle that has vertices at 0, 0, 1, 0, and 0, 1. Slices perpendicular to the x-axis are semicircles. Find the volume of this object. I'm going to start by attempting to draw a picture. So I'm told that the bottom of the object is a triangle. So one vertex is at the point 0, 0, another at the point 1, 0, last one at the point 0, 1. If I take this object and I slice it perpendicular to the x-axis, my slices are half circles, semicircles. All right, I graphed this object using a computer. I tried to graph it by hand right there so you can see my triangle, and then each slice is going to be a semicircle. I did graph it on a computer as well, just to give you a little bit better picture of what's happening here. So this is what our three-dimensional object looks like. And so the idea is my slices are perpendicular to the x-axis. So the width of each slice is a delta x, or a dx. That tells me that when I do this problem, I am going to be working in terms of x. And my integral is going to have a dx. I have to work in terms of x. So the next thing I'm going to do is figure out, well, what is the area of a cross section of this object? I know that the area of a circle is pi r squared. So the area of a semicircle would have to be half of that, 1/2 pi r squared. I'm going to see if I can write this in terms of x. We're working in terms of x. And so the diameter of each of these semicircles is represented by these little lines that I've tried to draw in yellow here. And so the length of my diameter is given by this diagonal line. And that happens to be the line y equals 1 minus x. I know it's the line y equals 1 minus x because I can visually see that my y-intercept is 1, and down 1 over 1, my slope is -1. So the length of my diameter is given by that distance, that function, y equals 1 minus x. So that means the radius of these circles has to be half of that. So my radius is 1 minus x divided by 2. So that means area of my semicircles in terms of x is going to be 1/2 pi times 1 minus x divided by 2 squared. I'm going to simplify this a little bit. That quantity, 1 minus x over 2 squared, I can just write that as 1 minus x squared over 4. And then we can actually multiply the 1/2 with the 1/4. Now I've got 1/8 pi times 1 minus x squared. And so that is a function that gives me the area of each of those semicircles in terms of x, depending on where we are in this object. So to find the volume, I'm going to add up those areas. So I'm going to integrate my 1/8 pi 1 minus x squared dx. And looking at my picture, we are starting at x equals 0. Our slices start at x equals 0, and they stop at x equal 1. So my bounds of integration are going to go from 0 to 1. All right, and this is something we can integrate. If you wanted to, you could FOIL out that 1 minus x squared. I'm just going to use a u sub. I'm going to let u equal 1 minus x. So then du is negative 1 dx. And I can rewrite this integral as 1/8 pi u squared times negative du, or negative 1/8 pi times the integral of u squared. When I integrate, I get negative pi over 8 times u to the third over 3, or in terms of x, that would be negative pi over 24, 1 minus x to the third. I'm going to plug in my bounds of integration. If I plug in 1, I get 0. And if I plug in 0, I get negative pi over 24 times 1 to the third. So minus that minus makes it a plus pi over 24, and that would be the volume of this object. Here's another example. The base of an object is under the region f of x equal 1 minus x squared in the first quadrant. Slices perpendicular to the y-axis are squares. Find the volume of this object. Once again, I'm going to start by drawing a picture. So I know that the bottom, the base of my object, looks like this parabola, 1 minus x squared. The minus x squared is what tells me it's opening down, and then that 1, it's been shifted up 1. But we're actually just looking at the portion in the first quadrant. So I've shaded in the region that represents the base of this object. Now, this one's a little bit different than the previous one because now I'm going to make my slices perpendicular to the y-axis. And if I slice this object perpendicular to the y-axis, I'm going to see squares. Find the volume of the object. So this time, because my slices are horizontal, perpendicular to the y-axis, the width of each of my slices is a delta y or a dy. So we're going to have to work in terms of y. This reminds me a lot of when we found area between curves, and if we wanted to slice the object horizontally, we had to work in terms of y. The same concept is happening here. The width of each of these little slices is a dy, so we're going to work in terms of y. Now, if each slice is a square, I know that the area of a square is side squared. And the side of each of these squares is determined by the x-coordinate. So the length of that, that base of that square is determined by my x-coordinate. But I'm working in terms of y. So I'm going to take my equation. I'm going to take my parabola, and I'm going to solve it for x. So y equals 1 minus x squared. I added the x squared and subtracted the y to get x squared equals 1 minus y. Then I'm going to take the square root. So x is plus or minus square root 1 minus y. However, since we're in quadrant 1, I know that my x's are always positive. So x is positive square root 1 minus y. That means the area of each of these little squares in terms of y is side squared, which is 1 minus square root of y squared. All right, so we're ready to set up our integral now. We're going to be adding up those areas. And square root of 1 minus y squared actually simplifies down to 1 minus y. So the quantity I have to integrate now is 1 minus y. And my bounds of integration are going to be y values. We're starting at y equals 0, the bottom of the object, and we're stopping at y equals 1. So my bounds go from 0 to 1. If I integrate 1, I get y. Antiderivative of y is y squared over 2. I'm going to plug in my bounds of integration. If I plug in 1, that's 1 minus a half. I plug in 0, I get 0. So final answer is 1/2. I'm going to stop this video with this example. We are going to continue this topic in the next video, but please let me know if either of these examples were unclear.